Okay, welcome to the sixth installment, although it's the seventh week of the course, of our tutorials for using R in generalized linear mixed modeling. So I'm going to follow the sixth chapter in the online book and will importantly point out, a few places where I found some of these resources. So what we're going to do is just go over the syntax and methods for fitting mixed models in R and just some resources for that. So first couple of things to show you are the FAQ that Ben Bolker, who is among one of the folks that maintains a couple of these packages, he's got a huge FAQ on random effects models, mixed effects models, which uh, all of which use pretty much the same syntax. So there's a couple of different packages. We'll use one of them, but this is a particularly helpful part. Model specification. There's all kinds of stuff in here about our should we keep a factor random or mixed, whatever it is we want. It's a great site. There's also an awesome Q&A on cross-validated, which is a site I love that I actually participate in, about what the difference is between nested and non-nested random effects. That's something that we won't deal with too much in this course. We're going to deal with nested random effects, but is it very helpful and important in other areas. So just wanted to call that out. So there are, again, a number of different ways that we can insert random effects into our regression models or linear models to form quote unquote mixed effects models, some of them being hierarchical, which is something talk about in subsequent videos. And there is a choice of different ways to do this. So the earliest package in R was NLME, nonlinear mixed effects. It's still very good, but there's a successor to it in terms of sort of, I guess I would say ease of use, and some of the speed is improved, and that's lme4, which is what we'll use in this course. GLMMTMB is actually really nice, and you will see a little bit of this in the last week when we get to logistic models, because if you are using a generalized linear mixed model like logistic with a, for example, with a logit link or a Poisson type model, this package is really optimized for those. We'll see that lme4 can sometimes break down in terms of, those models are very complicated computationally, and so this package was developed to help some of that. So I'll let you read a little bit about it. Again, it's really what people are comfortable with. It is a little bit easier to use. Again, it has some good defaults, but just like everything else, you've got to be aware of what the default settings are and when to change them. And for example, chapter 10 in the Faraway book does a really nice job talking about how it can be treacherous to actually do hypothesis testing, and at least in terms of some kinds of iterated tests that you might use in ordinary regression. And we're going to talk about that in the ninth installment, which will be week 10 of the course. Oops. So this week is just kind of to demonstrate some of these things. So first, we're going to focus on using the lme4, or some people call it elmer function, and contrast that with AOV, which is the analysis of variance function, which actually relies on the linear model function. Contrast those two things, look at the output from some of these models, and then explore a little bit about some of the information that you can get out of them. So it's really exciting that the NLME package contains a very famous sort of quote unquote data set that Raudenbush and Brick used in their book, which you will have, if you have not read already, some scans of the chapters of that book. It's a great book, and you can actually find out information about the studies that there was a large group of studies. So this is the Wikipedia about the high school and beyond data set. And there's some more information about it here at the website for National Center for Education Statistics. So it's actually a longitudinal study, but what Raudenbush and Brick did is they took a subset of it from the 80s from 1 year, with the main outcome variable being the student's math achievement, and it's scored using a standardized test. It's actually scored on the Logit scale. So it's similar to, well, for example, item response theory, but that's a logit is what pops out of a logistic regression model. Anyway, the point of that is that it's a continuous variable, and it's relatively normally distributed. So it's a really nice well-behaved data set to use to start to learn this stuff. So we'll use it over and over again, talk about it a lot more next week. This week, we're only going to be interested in the student's math score as an outcome, and the fact that students are naturally clustered in these 160 schools. Now, in the sort of regular lecture, basically the whole point of this part of the course is to kind of get you to understand that we have two choices if we want to understand or account for this clustering in any type of statistical model. Our first choice is that we can choose to model schools as fixed effects, and as we usually would do with a categorical variable, a factor. When there are so many categories, that's not usually helpful, although it can be done, and sometimes it is done. There's a large area, especially within econometrics and other places, where they do that. But here, what we're going to do instead is to think about the fact that really we're interested in the student's performance. We might also be interested in the average performance of students in a school. And we might want to explain the variability at both of those levels, right? So the key to random effects models, or mixed effects, so models with random and fixed effects, is that in ordinary regression, we have one source of sort of unexplained variation. And that source is at whatever level we've measured our outcome at. And we visualize that with residual plots and so on and so forth. In a random or mixed effects model, we realize that there may be interesting variation at more than one level in our data set. So in this case, variation amongst the students within a school, but then also between different schools. Right? That's kind of one way to think about random effects models. The sort of consequence of that, or what's intertwined with that, the chicken egg thing, is that also we might think that if we do have students in our data set, which they are naturally kind of in these clustered units, we might expect that two students in a specific school, that their math achievement outcomes may be correlated relative to if two students in two separate independent schools. So both of those things, that the second part then violates the assumption of ordinary regression, that the observations are independent and identically distributed. So if we have any type of dependency between observations in our data set, one way to handle that is with random effects, but then also on top of it, it's usually of interest to quote unquote partition those sources of variation at different levels. So again, between clusters as well as within clusters. So much more about that in your lecture from the last few weeks. This is just about the data set. So this is just code that you can use if you load the NLME library, and this code uses the dataplier package from Hadley Wickham. You can get this data set, and it exists in two versions as math achievement at the student level, and then there is a school level data set. And so this code just pulls it all together. And so once that is done, these are the variables that will be used for the next few weeks. You'll notice that there is a variable school, which is coded as a factor and is just a different identification numbers for the 160 schools. So school is now going to be used as a grouping variable. The difference between, say, school and sector is that school is a grouping variable that we are using, we're treating the set of schools as a random sample of all possible schools that we could have in our study, whereas sector is a fixed factor because we're interested specifically in comparing public to Catholic schools, right? So random factor, fixed factor. Right? Then we have the mean SES at the school level. So this is the average socioeconomic status measurement for students within a particular school. And notice, let's switch to R and take a look at this data set. So this is it here. I've called it HSB. This is the code you just saw up here. And so one thing I want to emphasize is the way that these data sets are, the way your data needs to be to use R to analyze in anything where you have random effects is in what we call this long format. So this is kind of, basically how you would organize it anyway. Where it makes a difference is if you have longitudinal data, but just let's take a look, right? So you'll see that school 1224 appears as the first 47 entries in the data set. So all of these 47 rows are the 47 students in school 1224 that are in the data set. And we can see that anything at the school level, right, public, right, that's a characteristic of the school. Mean SES, that's a characteristic of the school, which is just the average of these 47 numbers there. Size of the school is the number of students, 842. High percentage of minority, this is a 0-1 factor, so this is 0, so this is a school without a high percentage of minority students. All of those things are school level variables, and you see that for the 47 students in school 12224, we've got the same values in each of these 47 rows. You see that? Now over here, we have the student, so we've got student 1 is in school 1224, which is a public school with mean SES of negative 0.43, 842 students. It's not a high minority school, but this student is a female with this SES. This is her math achievement. She's not a minority. This is just a mean-centered version of SES, which we'll talk about later, right? So you can see that we have two sort of levels of variability. The school level, which these values only change for the 160 schools. So here's school number 2, right? The second school is 1288. Here's all those students. Third school. So those values only change at the school level, whereas within each school we've got different values for all the students. Okay, so that's what we mean, the two different sort of sources of variation, right? The schools are going to vary, and then the students within the schools are also going to vary. Okie dokie. So you learn a little bit about a very simple way to understand some of that variability, and that is by fitting what's called the one-way ANOVA with random effects. Very simple model, which you see here. So the LMER package, or excuse me, the lme4 package uses, and by the way, let's go ahead and uh, uh, attach this package. So if this is the first time you're using it, you're going to have to do just like you usually do. Packages, install lme4. We can do it that way and install, or you can simply just type install packages lme4. I'm not going to do it because that package is a little finicky, so I don't want to update it right now. I'll go ahead and load it there. It gives me some, yells at me a little bit. And I'm going to go ahead and fit this model, and we'll talk about it. So here we go, fit the model. And as you can see, we'll go back to the HTML, can read it a little bit better. We've got a couple things going on in the syntax, right? Just like before, I've got a dependent variable and then a little tilde, and then the right-hand side are the predictors. Now this looks funny. We have something new. We have parenthesis, we've got a number 1, we've got the mid dash, which for you guys is usually on, you have to press shift and the key that's above your enter or return key, right? So on my keyboard, the slash is that key. If I want the mid, right? Just so we know what we're talking about, we're going to call that the mid line, right? Mid bar. This is how we specify our random effects. This is how we say which of the variables is the random grouping factor, okay? And that variable always is on the right-hand side of the midbar, okay? So when I read this in English, this says the outcome is math achievement, and I want to fit a model just with a random intercept, and that's what the 1 is for, across school. So what that means, if we go back to the ANOVA notation, that means that what we're going to do is we're saying that a student's math achievement, so student I in school J, their math achievement is a function of 3 things. Right? We can basically take it apart, partition it into sort of 3 things. This constant called the mean, the overall grand mean math achievement for all students in the population, plus some effect or incremental change, or whatever we want to call it, some contribution from school J, plus some contribution from being student I in school J, right? So our random effect is here. And in fact, we have another random effect, errors, which we called errors or residuals in ordinary linear models, are random effects. Right? They're random variables. Now what we're doing is we have another, basically residual, right? Something else that contributes to student Y being different from the overall mean level of achievement in the population. So to fit this model, we need to have an intercept that's randomly varying across schools. And so we'll see a different way to write down this model next week, in which we basically have, for each school, we've got a separate regression model, and then we squish them all together, so that what we're fitting then is we get an overall intercept across the schools, which is a weighted average, and then we get a variation, variability in the school level random effects. So how variable are the means, are the mean math achievement across schools, and then that residual variation, which is what the leftover, the variation within each school. So to do that, I type this model, identify the data set, and I'm done. So the summary command, so just to show you, I like showing you stuff over here, right? You'll fit, it's a big model. It's actually got a bunch of crap in it that we can extract. And we're going to just extract the summary. So summary odd1 RE. And let's take a look at it. So very similar to what you've seen before. It tells you what it is. It shows you the model, the data set. We'll talk about some of these things here. It gives you a look at scaled residuals at level 1. Now it's got a new thing. Okay? It's got a section for random effects, and it's got 2 lines. Okay? The first one is and we don't see the actual, so it's different than fitting a fixed effect where we have a beta or a regression coefficient for that fixed effect. Instead, what we do is we treat the random effects as nuisance parameters, and we try to just estimate the variance. So in a model without a fixed effect, so there's no other predictor in this except for the random effect of schools. So you see down with fixed effects, we only have intercept. So we're only estimating the model intercept, which until this point in your life has never been interesting, and now is an interesting piece of information. Okay? So we'll get there in a second. What we first get are the variance across the schools in terms of their intercept. And what an intercept is in this model, because we specified it this way, is the school intercept is literally the school mean math achievement. So this is saying that there's some variability across schools in the average math achievement of the students in that school. Not surprising. And then down here we have the leftover residual within school. So we can see that, not surprisingly, and this is generally going to be the case, that the variation in the mean level of math achievement across schools is going to be smaller than the variation of the single math achievement scores within a school. And we'll see how to use that information in just a second. The fixed effect now is just the intercept for the model, but it's an interesting piece of information. It's actually an estimate of the population math achievement, right? So it's an estimate of all of the whatever population of students this study represents. This is a new estimate of the mean level of math achievement for this population of students. Now, as you'll see in the tutorial, and I want to show you in my code here, it lists us at again, it's on the logit scale, and then it's sort of transformed. So 12.637 is not a meaningful number. But importantly, I want to show you that it is a different number than the mean. If we were to compute across all 7,185 students in that data set, the average, the sample mean for that n equals 7185 data set is a different number. So why is it different? It's different for 2 reasons. One, the schools each have a slightly different number of students, so the number of students per school is slightly different. So each school had a slightly different number of students sampled. 2, there's variability in the average across schools. And there's also going to be variability within a school. And so that actually relates to how reliably the school's mean can be estimated. And the reliability of those school means contributes to this estimate. So this estimate of math achievement is slightly lower than this one because it's weighted in terms of the schools that have higher precision. So what does that mean? Precision in statistics is a term that means the reciprocal of variance. So if you measure something with high precision, then you're measuring it with low variance, which makes sense, right? High precision means you've very precisely measured this thing. It's not gonna, it's not varying a lot, and so you can be sure that your measurement is reliable. It's not gonna jump around next time you measure it. So the estimate of a fixed effect in a mixed effects model is what we call a precision weighted average estimate. And we'll learn more about that as we go a little bit there. So just to show you kind of in parallel to what Faraway shows you in the book, we could fit this model in this way using the ordinary ANOVA syntax. But we would not do that because this is not an ANOVA estimator. It's actually estimated using maximum likelihood, but in fact, it ends up being a weighted least squares estimator. And that's important just in the history of random effects models. The ANOVA estimator is easier to compute, but only works when you have equal group sizes. So just to show you here, that the mean square within is about the same as the residual there, okay? But the school mean square is much different. Okay? So we've got slightly different pieces of information coming from different places. And so that's just, a reason not to use the AOV. But sometimes, for quick and dirty methods, you can do things this way. All right. Another thing to point out is that the default method for fitting linear mixed effects models with Elmer is to use, if you looked here, it says REML criterion. REML is short for restricted maximum likelihood, and this is covered in the text. But I just want to show you how to turn that off. So you can use what's called unrestricted or full maximum likelihood estimation. And in fact, you should do that. And by default, for model comparison, your model will get refit this way. Anytime you're trying to compare models with different fixed effects, so doing any type of nested model comparison. In a lot of cases, it's not going to make a big difference. So just to show you here, if we refit this model, but the argument RMEL is set to false, meaning we fit with regular maximum likelihood, okay? We'll see, now we get more information. We get AIC, BIC. So this is a full likelihood. So we have a log likelihood. We have a deviance here. The scaled residuals are about the same. Both of these numbers are almost identical. So the school level variance is a slightly different number, so 855 versus 8.64. And so the estimate of the intercept is just slightly different. And then we don't get this information from a REML model. Again, without diving too deep into theory, REML is used usually to specify the fixed effects, or excuse me, the random effects. It's a little bit more stable, especially in complicated models. And so if you want to use hypothesis testing or some variant of it to first figure out, do I need additional random effects? And I'll talk about what those might be in the coming weeks. So you want to compare two models, one with and one without a specific random effect. You want to use the REML estimator. So you want to not type this. You want to use this syntax. So we don't have any REML false here. That's how we want to test different random effects structures. Which again is a little treacherous. We'll talk about that in the coming weeks. And then to interpret your coefficients, maximum likelihood is probably a little bit better, but usually what happens with REML is that part. It's a complicated procedure where the fixed effects are then refit with maximum likelihood. So for interpreting the fixed effects as you would in an ordinary regression, you can do either one. Another thing I want to talk about quickly, and let's shift back to the HTML here, is that one of the main outcomes or reasons why you would fit that relatively boring model without any predictors other than the intercept is to estimate what's called the interclass correlation. The interclass correlation in a random effects model can be a useful way to kind of determine a couple of things. One, do I really need a random effects model? And two, what if I'm interested in, so in this case, if I want to perhaps do some hypothesis testing about whether, again, say Catholic versus a public school would have a different average math achievement. I want to look at this number because the larger this number is, the more variability there is at the higher level, in this case, the school level. So let's walk through a couple of pieces of this. So the computation of interclass correlation is really easy. It just takes two pieces of the output that we've already seen. So we want what's called the sigma squared alpha, or we'll have a different subscript for that next week. But this is the variance of the random effect for school, which we already saw before. I'll just the model summary again, is 8.614. And the other number, sigma squared sub epsilon, is the residual variance, 39.184. If I take the variance of the school effects and divide that by the total model variance, which is school effects plus residual, I get 0.18. This can be interpreted as a proportion of variance or as a correlation. So you could say 18% of the variance is at the school level, or you can say that, given if you randomly select two students from the same school, this is about how correlated their math scores should be. So it's not a very large number. It's pretty common. Very, very large interclass correlations outside of longitudinal data are not very common. It's, anywhere from like 0.03 to 0.2 would be common in educational settings, maybe in healthcare. It's sometimes smaller. So it's not the only way to determine whether random effects are needed. In fact, most people would argue if your data are clustered in some way, random effects will at least make your inferences better, even if you don't care about predictors at the different levels. So this is just one way in an ordinary mixed effects model or random effects models, you can get some information about the dependency of observations within a cluster. Another thing I want to point out right now is if you'll see, this will be more obvious when we have more predictors in a minute, but you might have noticed in the fixed effects here, we have our estimate. Even though it's an intercept, it's still an estimate. It still has a standard error. It's a t-value. And in ordinary regression, we'd have a p-value column here. Right? It's not there, is it? It's missing. And we'll see, just as a preview, here's a slightly more complicated model we'll fit in a minute with an actual predictor. In this model, we ask, what's the relationship between a student's socioeconomic status within a school and their math achievement. And we can see, again, estimate, standard error, t-value, no degrees of freedom, no p-value. What's going on? Again, without getting into it, there are some reasons that it's not there. We'll talk about in a couple of weeks. But one way to get around that is to use confidence intervals for inference. And you can actually do that for the random effects too, although one issue with random effects models is the hypothesis of zero variance at any level is pretty untenable. And in fact, if there is variance of zero, that's a real problem for estimation, which I'll leave for later on. So if you want confidence intervals for all of the things in the model, in this case, the two random effects and the fixed effect, the intercept, we're just going to focus on the intercept right now. And you want to use bootstrapping rather than normal theory or the profile likelihood, which sometimes is a little bit better. However, I will caution you. So this is a relatively simple model with not a very large data set comparative to other data sets. And so I'll just show you on my machine, which is getting a little old now. Let's just see how long it takes to compute. So if I click play, you can see it thinking, computing, And so that was, not an instantaneous computation. You will find if you start adding predictors or with a larger data set that you might wait for quite a while to get those bootstrap confidence intervals. Why? When you bootstrap, you're basically resampling the data set and fitting a model over and over and over and over and over and over again. So with simple models, small data sets, that doesn't take a lot of memory or computational power. With larger data sets, complicated models, it adds to the time of processing. So just a caution if you're just willy-nilly typing method boot, it can be a little treacherous. So we can interpret these confidence intervals as we like, right? This is giving me a piece of inference about our estimate of mu, the overall average math achievement in the population of, say, fourth grade students, right? That it's, we have 95% confident that it's between 12.09 and 13.17 on the logit scale. We've also got confidence intervals for the two variances, although they're here as standard deviations. Right, so if we look at our model output, we'll see variance, standard deviation. All the formulas are in terms of variance, but computationally standard deviation is easier to work with. So you see this is a confidence interval for the standard deviation of math achievement across schools. This is a confidence interval for the standard deviation of the residuals across students. One thing you can do with the output is and you don't do this with the confidence interval, you would go back up to the standard deviation. In normal statistical theory, right, we can plot a normal curve with a mean and standard deviation. So now we have that, right? So we have an estimate of the mean level of math achievement across students, and then we have an estimate of the mean math achievement across schools, but also students within the school. And then we have a standard deviation for this so we have a mean and standard deviation. We can basically fit a normal curve. And so I've done that here. And this is to sort of emphasize that one of the assumptions of random effects models is that the random effects are normally distributed. So the implicit assumption we make is that the schools in the population, and so the 160 that we have sampled from the population, come from a truly normally distributed population, right? That the most of the random effects are small, so most schools are within. So normal theory tells us that about 68% of the normal distribution is between -1 standard deviation and +1 standard deviation. So we might say about 68% of schools in America in that period of time had average math achievement scores of 9.7 to 15.8. Notice that this is not a confidence interval. Confidence interval is different. Confidence interval gives us a way to make an inference just about the mean. What I'm doing here instead is using information from the model as a description of the potential population behind this sample of schools. Okay, so it's very important to disambiguate that. Finally, just to show you, and we'll do much more on this in the coming weeks, I just did want to show you, if you were curious, we can then add fixed effects to our models just by putting in the predictors, right? So here we're now we add, in addition to a student being in a particular school as an explanatory factor for their math achievement, which we treat just as a random variable. Now we have a fixed effect of socioeconomic status. So here we're saying we're able to fit it. We'll have a regression coefficient that goes along with that. So interestingly, we'll talk about this later. We can kind of compare variances between different models to talk about sort of like a quasi variance explained R squared, but that doesn't fit in very well here with random effects models, but we can get some information out of that. So when you fit different models, you're going to expect this is now conditional or residual variance. So conditioned on this level 1 predictor. Here's my school level and residual level variances. Notice the school level variance didn't change much because CSES is not a school level variable. It's a within school variable. So you could see that really what's changing and getting a little smaller is the residual leftover variance about the residual sort of the leftover unexplained information within for a student within a school. And then down here, as we usually see, we actually have our regression coefficient for this is a centered version of SES. It's centered meaning that within each school, a CSES of 0 means their average. We use centered predictors often in mixed effects models to keep the intercept interpretable, but you don't have to always do that. That's important if you have predictors at level 2, which we will have in later weeks, but we'll put that aside for now. We've also, this is something we'll get into, the CSES effect is also assumed to be the same across all schools. We don't have to have that be the case, but in this case it is. So this is fit very much the same way it would normally be fit in an ordinary regression model. So for example, we can just fit an ordinary regression model, ignoring the fact that students are clustered within schools, and we see an almost identical coefficient, but we see a different standard error. And we see a different t-value. We also see much larger residual variances. Okay, that's because we have not baked much larger residuals, so a larger residual variance, because we have not baked in another explanatory effect for the students, which is that different schools are going to have different levels of math achievement, and that's a big explanatory factor that's missing from this model. But interestingly, not a big difference in the estimate and the standard error between the two models. But as models get more and more complicated, you can expect some differences between the two. Okay, so this is not how you would want to approach this data set. It's just an example of how of what will happen if you ignore the grouping structure. All right. One final thing is, we talk about random effects, but we don't see them. What are they? And you can pull them out from the model in a nice, easy way. So let me show you how to do that. Let me scroll all the way down. I'm going to go ahead and fit, we've already fit those models. So a random effect is simply a residual, right? So there we go. So if we looked at this, and it's hard to see there, so we're going to pick it out. So we're going to look at the random effects for the first 10 schools. And I'll put them up there. So what is this telling me? This is basically just saying, what's the deviation from the grand mean for this school? Oh, well, this school is about 2 points less than the average. School number 2 is a little bit higher, better performing than average, lower performing than average, better performing, lower performing, so on and so forth. Right? And we can actually see that. So the random effects are residuals, right? They're either negative or positive with their expected value 0. So it's basically just the amount in this model, not all the time, but in this model, is simply the amount by which the school deviates from the estimated overall mean for the schools. Now we can use that to estimate a school's mean. Now again, these are not the actual means of the scores within the schools. They're what are called empirical Bayes estimates, which means that let's say I run, and this is kind of comes from complex surveying and ways to efficiently estimate population values with limited samples, right? So let's say I'm at a small school, or let's say I'm at a big school, and only a couple of, maybe 12 or 13 of my students are in this data set. But I'd like to estimate the overall math achievement at my school. Using a random effects model, what we do is fit the model. So we use the coef function to extract the estimates of the actual, in this case, the school intercepts from the model. And so I can see that school, whatever this first school is, which had a random effect of negative 2.663, we would estimate the average math achievement for students in that school to be 9.97. So again, these will not be exactly equal to just the simple average of the students in that school in the sample, because what happens is for either small schools with small sample sizes or schools with a lot of variability, essentially our estimates here borrow information from other schools that have similar random effects. Right? So school X, which might have only a few students in the sample and is measured poorly, we could still make an estimate of their average math achievement by using information from the other schools that are like it. And that's kind of I suppose, the intuition behind empirical Bayes estimation. So just an example, right? The mean math achievement for school 1303, which I think let's see if I can, I'm pretty sure 1303 is this last one, is 16, let's see. Here it is, right? So school 1503 is this one here, is 1, 2, 3, 4th in the, well, we see that we would estimate it's the mean math achievement of students in that school at 15.59, but the actual sample mean for students in that school is higher. Okay? So again, what's going on? This school may not be estimated well. The variation may be too large. And so what happens is that this sample average, 16.225, is shrunk or becomes closer to the population average of 12.1. 6.4, because the way that the calculations work, either the variance is very large in that school or there's not a lot of students in that school. All right. Okay, well, I think that's enough for this time. So the important things were just to get a feel for lme4 and contrast the restricted and ordinary maximum likelihood. We saw the output from those models, how we could use it for intra-class correlation, as well as a little bit about the random effects and their estimates. The next few weeks will be all about how do we use these models to actually examine our research questions, test hypotheses, make better estimates, and that's what the rest of the course is about. All right, well, see you next time.